everyone, so this is my second video in the series about classical mechanics. In the last video, I gave you a quiz question and you might be hungry to know what the answer was. Well, I did the math and I figured out in the first leg of the journey, the velocity is 1 meter per second. In the second leg, it's 2 meters per second. And in the whole journey, the acceleration was 1/3 meters per second squared. Now, with the challenge covered, let's now go on to Newton's laws. Now, you might be thinking, what are Newton's laws? But before we talk about that, let's back up and talk about forces. Now, what are forces? Pretty much anything that makes a thing happen is a force. For example, when you walk, your legs are exerting a force on your body. When you jump, your body is exerting a force on itself, but your earth is exerting another force on your body, making you eventually come back down. Now that we covered forces, we can talk about how to measure them. Forces are measured in newtons. 1 newton is the amount of force you need to move a 1 kilogram object at an acceleration of 1 meter per second squared. In fact, holding up an apple has 1 newton of force. So I agree, we have a lot of force in our bodies. So now let's talk about net force. Net force is just the sum of all your forces on your body. It can be useful when there are more than one force acting on your body. For example, when I was jumping, there are 2 forces on your body. The jump force and the earth force, which we call gravity. Now, so we have these 2 forces acting on me. We need to combine them to figure out exactly how I will jump. Now, we can simply do that by adding the forces together to get net force. That's just it. Now we talk about net force, we can move on to Newton's laws. So, what is Newton's first law? Oh, wait. Who is Newton? Newton was the guy who came up with all this force stuff. If you notice, the basic unit of force is called Newton. So, yeah, this guy is pretty famous in math. So, let's go back to Newton's first law, which states that, objects love to do what they are doing. For example, an object that's still likes to stay still, and it can only move when you give it a force. Similarly, an object that moves likes to move, and you can only stop it from moving when you give it a force. The thing that makes still objects still and moving objects moving is called inertia, and the measure of how much force it takes to change an object's inertia is called momentum. Momentum is just the mass of an object times the velocity. Momentum is pretty interesting, and here's why. Say you have a magic bubble encasing a tennis court, and that magic bubble, no energy can pass through it. So all the energy that's already inside the bubble stays in the bubble. Now the tennis court inside the magic bubble, the ball in the tennis court will have some momentum. But here's the thing, the ball's momentum, or more precisely the ball's momentum combined with the momentum of the tennis rackets, the tennis court itself, the stadium fans, all the momentum combined will always be the same if the magic bubble remains magic. But if the magic marble is taken away, momentum can be lost via heat, which is why you don't see the conservation of momentum happening in some situations. It does happen in other situations. For example, in the tennis court example, very little energy is lost as heat, so you can definitively say that momentum is conserved. Now, to the second law. The second law is pretty simple. Force equals mass times acceleration. That's pretty easy to draw inside of a bit. Remember in the last video I used the formula of acceleration, that is final velocity minus initial velocity over time? Well, we can just plug that into the acceleration rate of Newton's second law, do a bit of maths and come up with this. Force equals final momentum minus initial momentum all over time. But wait a minute, if you saw last video, that means that you know that what we have here is definitive proof that force is a derivative of momentum. So yeah, it's pretty easy to draw insights from the second law and Newton's laws in general. So now on to the third law. The third law states that every action has an equal and opposite reaction. Do you mean by this? Well, you might have seen that while people are swimming, instead of pushing themselves forward, they push the water backwards. How does that help them reach the finish line? Well, if you imagine this cupped hand as the pool and this as the swimmer, then you can see that if he pushes the water behind, he can reach the finish line. Now, so what's interesting is that the force, the reaction, the thing that the swimmer gets forward is equal and opposite to the force the swimmer pushes to the water. You may have noticed that equal and opposite is an oxymoron. But that doesn't mean that Newton particularly loved oxymorons. It's just because he was trying to say that the forces are equal, the directions are opposite. See, just like the velocity from video 1, the forces are vector quantities. They have both a magnitude and a direction. So that is why it's equal and opposite. Now that we know all of Newton's laws, we can go to the challenge question. A diver who weighs 1 kilogram is diving and he's pushing back the water at 3 meters per second squared acceleration. Now, using Newton's third and second law, calculate the force that the diver is applying and the force that will push him to the finish line. So that's all for this video.